Good morning. Welcome to the TVR off. I have a speaker that needs to be turned off. I'm Lou Berger. This is Russ White. We're co-chairing. And we also have Ying Zhen Ku here with us, who's volunteered to act as our secretary. Thank you. All the material is online. And if you're interested in the topic, please take a look at the material. We also have the standard web page available that summarizes the purpose of the BOF. We'll of course go over that here. And we have a couple of drafts even, although they're a little bit early. Next. This is an IETF meeting. All of our meetings are governed by our Note Well, which has rules regarding our participation. Basically, everything you say here becomes a part of our permanent record. If you're not familiar with the Note Well, please go to the IETF page and take a look and familiarize yourself with our rules of participation. Next. We also have rules related to conduct, and basically we ask you to always treat each other with respect and be professional with each other. Of course, it's okay to have good technical argument, but please keep it at the technical and professional level. And of course, we have a document governing that too, PCP 54. Next. For those in the room, we ask two things. The first is please scan the QR code, join the online tool, whether you use the phone or the computer. It's really important because of two things. It gives us our blue sheets. It also allows you to participate in polling, and we will conduct some polls later in the session, and we'll do that versus raising hands or humming so that we are equitable to the people who are remote, so they can participate at the same level. For remote participants, you're here. Thanks so much for joining, and please mute your mics if you're not speaking. The only additional piece of information on this slide really is come join us on joint minute taking. So we use HedgeDoc, Etherpad, whatever you want to call it. It's a collaborative tool where everyone can make sure that we're capturing the conversation and the discussion that happens. You don't have to capture the material on the slides. That's already on the slides, and we have YouTube available. But for the discussion, it's really important to help capture the discussion. Going back to the scanning in for on-site, I forgot to mention the other bullet that's on here is the IETF requests and requires that you wear a mask in the room, and the only time you should take it off is if you're at the front talking.
When you speak at the mic, please make sure you give your name before speaking, because the people who are taking notes and people who are remote often have a hard time distinguishing voices in our current environment.
And we are going to use the Meet Echo queue for controlling discussion. So if you want to come speak at the mic, please enter the queue, and that allows us to make sure that we're taking remote comments at the same level as in the room comments. Next, please. So what are we doing here? You're going to hear in a moment about the problem we're trying to solve, but from sort of the administrative side, we're trying to answer a few questions. First, what's that problem? Rick is going to talk about that. And then we also are going to follow up the problem statement with some use cases. That really drives our requirements, helps us better understand the problem we're solving. Eventually, we have to figure out what new work is to be done, where the gaps are in the existing technologies. And those two are sort of the main purposes of the discussion. But from a management standpoint, from the ISG, from the IAB, a very important question is there sufficient interest in working on this problem at the IETF? So at the end, we are going to have a poll that says, are you interested in this topic? And are you willing to work on it? And ultimately, those are the questions we're here to answer. So yes, we want to understand why we're here, what problem we're solving. But from an IETF standpoint, do we have enough people to work on it?
Yeah, not just what you're interested in, but please, if you're willing to work on it. If you're just interested in the problem, that's not really useful to us. What's really much more useful is, yeah, we're willing to write drafts, edit drafts, do code, whatever is needed.
So we have a posted agenda. The agenda is a little different today than it was yesterday or the day before. Um, Basically, we got a little more information and some additional contributions. That's always really appreciated as a contribution-driven organization. One thing I want to say about the time here, these are approximate times. We have a good 30, 25 minutes for discussion. If that discussion happens earlier in the session, that's okay. We don't have to be completely rigid to these times. We will sort of manage the cues, manage the discussion so we can cover all the topics. But if we have a lot of discussion, let's say on the problem statement, we'll let that go over and we'll just take from that open discussion time. And with that, we're going to jump over to the next. Rick Taylor is going to talk about the problem statement.
Morning all. Oh, that's very loud. Good morning all. So I have a published problem statement, which I'm not hugely proud of. It was pretty much a stream of consciousness done pretty quickly. And off the back of that, had very productive meetings with a number of people who picked up on that. There was good correspondence on the mailing list. And I want to call out Adrian for taking me to one side yesterday and saying, let's drill this down to something a bit more short and tight. And that really hasn't been updated yet and is kind of the content that I will come up with at the very end of this slide deck. But meanwhile, can we have the first slide, please? So I'm going to jump straight into the meat of it. As I and several other people we have chatted to see it, there is the following problem. We understand that in routing, you have nodes, you have links, they come, they go. You need a protocol to try and build some sort of topology so that you can build end-to-end paths across these networks. We can do that fairly effectively at the moment. But in general, we believe as we're building those protocols that we must react to failures in these links in order to recover, in order to maintain this topology. What we are discussing here is the proposal that maybe there is another case here, which is these links and these nodes may change in predictable or schedulable ways. So you can know with a certain degree of confidence in advance of a break or a restoration in link, adjacency, or whatever, that it's going to happen. Therefore, as a routing protocol implementation or a protocol design, you don't have to react to it happening. Oh my God, my link's just gone. You can say, oh, at 12 p.m. on Wednesday, that link's going. So I can pre-compute an alternative, or I can keep a backup topology ready to apply, or I can do smart things, and I'm not entirely sure personally what all of those smart things are, but I would see that as an interesting area to investigate, so that when that scheduled event occurs, you are ready to do it, and you can move swiftly on without losing end-to-end connectivity, your traffic can flow, less disruption, etc. So next slide, please. So I'll give you a second just to read through this a little bit, but the obvious answer to that statement is people come back and say, well, actually routing protocols already handle convergence when we lose links, when nodes fail. And in general, that convergence is fast enough and fast reroute mechanisms exist and they're good. We've worked on this for donkey's years within the IETF. We've got a good suite of protocols that will pretty much do this. But as I've said before, routing does not currently handle the potential connectivity represented by route nodes and links that are scheduled to turn up in the future or are scheduled to disappear. So you know it's going to happen, it just hasn't happened yet. And I personally see that as a critical difference. So, and that third point is basically an extension of that, which is not only do we don't handle the fact that we know a node is going to appear or links are going to become available, we also don't handle the fact that we know they're going to disappear as well by extension. Next slide, please. So the problem is, if we think there is a use here for having this a priori in advance knowledge of changes to the connectivity and the adjacency and the availability of the individual nodes that make up the network over which we're building a set of end-to-end paths, how would we solve that? Do we understand that there is a problem to be solved here? Because again, this is problems. So how does a node or link that is not up have its presence advertised? How do we inform a routing protocol that something is going to occur in the future? And how, if we can say it's coming, can we also include how long is it going to be up for? And equally, the converse. So can you say, at this point in time, something is going to happen. Either an availability is going to arrive or a link is going to disappear, so therefore service will not be available across that adjacency. How long is it going to be for? And will this repeat? Will this recur? How long is this whole description of forthcoming events going to be valid for? So we're sort of starting to talk about, is it possible to describe a schedule? And that's the word I'm using at the moment. I'm not trying to impose any words onto any future solution to this problem. But can we talk about scheduled forthcoming events? And is that of use to routing protocols? Do we see advantage of doing that? The follow-on question for that is, if we see available and unavailable as one of the things you would describe in that schedule, could we say, well, availability could just be seen as a Boolean metric, up, down? Could we say change link costs? You know, whatever the weighting you're using to build your shortest path across your available graph, could we say at some point in time, the cost of this link is going to change? So you can go and run your Dijkstra algorithm well in advance of this and say, well, I know when that time occurs, I should probably, my shortest path tree is now something completely different. I could pre-do that work. Next slide, please. Okay, so this is the full text, and I'm not going to go through it again. I've broken out the key points in the previous 3 slides, but that's there, so please grab it, read it through. My intention is to work with Adrian to reintegrate this text into the existing problem statement and to update it if there is a general consensus that we want to continue working on this, and there is such a thing. I apologize, I didn't have time to get this back up onto GitHub, etc., etc. And I believe that is the last slide, because I've split this to talk about existing technologies and a bit of scoping to go later in the agenda.
You.
Kevin is heading to the mic.
It's a tall one. Hi, Kevin Fall. Did a little work in this area about 10 years ago. I just wanted to, some comments,
Sure.
observations. So interestingly, you know, we can trace routing we do in sort of internet and whatever to some work that had been done. You mentioned Dijkstra algorithm, for example. So 1958, there's a publication, Flows Over Time, from Ford Fulkerson, which is the same origin story that we have for, you know, regular kind of routing protocols. So I think when I first came across that text, it was interesting to me that it was really so old. But just some other comments that I would concur with you. It's sort of a different problem space from a kind of graph theoretic point of view, because you have a time dimension and all of that. Whether it's useful in this context, that's an important sort of debate to have. But I guess I would just say that there is a lot of academic work in this area, but it uses words that we don't tend to use here. And it also, just one other little thing, sort of meta thought about routing. You know, when I went through school and learned about routing, it was presented like, you know, here's link state, here's whatever, distance vector, etc. But there's another whole world that looks at the same problems, which was the operations research community and their research, and it's optimization problems, and they're duals. They're really the same kind of problems in many cases. And so if you, the other kinds of interesting work that relate to this, that probably is not an IETF scope, but just to give you some thinking, is like dynamic transshipment problem, things like this. Is where you have you know, warehouses and highways, and the highways are fast or slow, and the warehouses have so much capacity, and you need to get certain you know, commodities from one place to another. And those were the types of work that we were thinking about, whatever, 10 years ago, when like, oh, we have links that come and go, but what's going to happen with the data we care about if it has to go a long way? Maybe it has to camp out somewhere. And so if, you know, that's a pretty different thing than what internet architecture usually does. But you could imagine a world, and I think Dave Clark said this once, like, oh, at one point we were thinking that packets could just live in a buffer for a day. Okay, so just, I don't know if any of that's going to be in scope, but I just want to sort of throw out, there's a rich area that we don't normally tread in here in this place.
Two quick answers. First off, I think the presence of existing research in this area is a really good thing, because I always worry when I think of something and everyone says, that's unique, no one's ever thought of that. It probably means it's really dumb. So the fact that other people have been spending years, decades researching this stuff, I think that's really useful. And second of all, I'm going to come back to a bit of the technology piece and look at some of the gap analysis stuff in a later presentation. We've scheduled it in fairly bite-sized chunks. And you're right, there's what we do in the internet area, particularly in pretty stable networks that we're all pretty familiar with. There's the whole MANE piece I want to talk about, where there's a different approach. And you're right, the kind of generic traveling salesman problems, the resource scheduling across routes that are not traffic-based, there's a whole wealth of stuff there. And having some kind of timetable. I mean, think about railway systems. They have a timetable, so you know where to get there. Get to the station at this time, because that's when the train's going to be there.
See if the internet goes on strike.
don't go there.
Just as a heads up, we do have some extra time for discussion, but we also do have 8 people in the queue.
Oh
so we should keep things moving along. It's good to get the points, but let's not spend the whole time on one.
So this is Alex Clem, FutureWay. I have one question to the problem statement. So I understand the basic premise of this, but I think the second part is missing, namely what you're actually planning to do with this information. So assuming that you had this solved, how will you leverage it? How will this be better? What problems do you solve better by knowing the schedule in advance versus having to reconverge or what have you? So I did not really see this explicitly mentioned. Maybe it's implied in your mind, but I think it would be helpful to be explicit about that.
Fair criticism. You're right. That first off, the problem statement can be much better. But the quick answer is, I think there is an opportunity. If we know something is going to change in advance, then we don't waste time and possibly precious resources trying to work out why it failed, trying to bring it back, because you know it has gone. No need to try and restore that peer link. No need. So that's one opportunity to not waste scarce resources. And the other opportunity is, if you know something is going to happen in advance, you can do that calculation as a low priority because you know how long you've got to do it. If particularly when we're looking at IoT, anything in space, general resource constrained things, anything we can do to save on conservation. So if we know something is going to change, we can do the calculation now rather than have to rush a reaction to something happening. We can be sensible about the resources we allot to making that change because we knew it was about to happen.
Right. So we're going to move on to Tony. Tony, go ahead.
Juniper. Sounds like we've got an echo.
Sorry about that, Tony. You can go ahead.
So my concern was something we raised on the mailing list, which is, are we covering dynamic topology? I think if we are not covering dynamic topology, then the problem is relatively straightforward. We already have techniques for dealing with links that we think we're going to take out of service. And being able to do that on a schedule sounds like it's pretty straightforward. If we are planning on bringing links up, then we have a question that was not dealt with on the mailing list, which is, do we wait for actual liveness information to propagate? i.e., if the link is scheduled to come up, does it actually come up 100% of the time at the scheduled time? So that seems like an important question.
So
I'd really like to focus on the dynamic topology question.
thanks, Tony. I'll try and answer some of those quite quickly. So I'll start with the second point, which is, if a schedule says a link is going to be up, do we always believe it? I think would be a mistake. I think experience tells us that you always have to deal with exceptions. You always have to deal with unpredictable failures. We do that with all the routing protocols from across the entire spectrum of dynamic to very stable environments. So I'm not suggesting that you don't expect failures if you have a schedule. I think that's naive. The dynamic question, so that's a scoping question. My gut tells me you try and start with the simple cases and then expand out to the more complex ones when you have a better handle about your approaches. But that doesn't mean you don't discount more complex cases while you're looking at your simple solution. That is a very politician's answer to that question.
Yeah, I think you might have missed each other, because you have on your slide, I think, the answer to his question, which is dynamic topology is in scope, and that's represented by that T2 and T4s. At T2, you had a break along that path, and then at T4, it comes up to a different, your adjacency goes somewhere else. So I believe, and Tony, you can jump back and answer if I get that wrong, but I think that's what you meant by dynamic topology. So there's a change, not only is there a change in link status that's scheduled, but there's also a change in who you're talking to.
Yeah. No, if that is our definition of dynamic, then yes, absolutely. I come from a Manet background where dynamic can mean almost chaotic. And those edge cases, I would suggest, still remain out of scope when everything is moving at such speed, or your schedule is talking about nanoseconds, and the predictability of this stuff becomes very low probability. I think we disappear into a corner case we shouldn't go in. But yeah, links up, links down, nodes coming online, nodes moving relative to each other within a potential topology. That level of dynamism, absolutely. If it has corresponding predictability.
Okay, moving on, Eric.
Thank you. Yeah, I just wanted to make a comment from relay a comment from a colleague of mine, which I think echoes a comment that was made at the mic earlier, and also by you, Rick, that it's like bus scheduling or train scheduling, or using a Maps app. It's related to driving directions, but it's also sufficiently different that it warrants a special look. And so, for the purposes of like BOF working group formation, I think it's worth recognizing those differences and having a dedicated space to concentrate efforts on that.
Brilliant. Thank you.
Julian.
Julian Luchek. So this BOF is actually quite timely for me because I came across a situation recently as follows. So you have a network in which there are a number of remote sites. And so in the main part of the network, let's say you've got a router R1, which is connected to a remote site. And in remote sites, you've got routers R2 and R3 facing the main network. But there's only one fiber connection into that site. And so what you've got is a fiber switch in the site that connects the fiber link normally into R2 on that site. So R1 is normally connected to R2. But if R2 should fail, there's some automation that makes the switch flick over to R3. Now, R2 and R3 are connected to each other, and there's some other routers behind. So R3 knows as much about the topology as R2 does, even though it's not connected at the moment to the main site. And so with current, protocols and so on, it's frustrating that, take of order a few seconds for, R2 to come up, the protocols to come up, etc. So this, sort of chimes in very well with that scenario, in fact.
Thank you. So that I think is yet another example of reducing the loss of data transmission capability when something has happened. if you can know it's happened in advance, then you can say, well, as soon as that goes, I know what it was expected. That's usually R3. R3's warm standby and ready for it rather than coming from cold. And I know that existing protocols have mechanisms to make this work. And just genuinely, I don't know if this isn't solved. And if sufficient people stand up and say, we've got solutions to this, I will be very happy. But I don't think we do, or I might not understand. So thanks.
Andrew?
Hi, Andrew from Liquid Intelligent Technologies. So I live in a part of the world where power is not always the most stable. Luckily in Kenya, it's more stable than my colleague from South Africa. I think he brought the power load shedding with him with that power outage when we arrived. But here's the thing. Yes, I can say the thing's going to go down. We've got the fast reroute, etc. However, if I get an outage and I know that this is power or has a good probability of being power based on the schedule, and I'm just interestingly enough was looking at the load shedding for my parents' house, and they 3 to 5:30 and 7 o'clock to 9:30, blah blah blah. How I'm going to react to that based on, is this power or something much more temporary? How long that power outage could be could potentially be very different.
Mm-hmm.
And if, for example, I've got someone at the NOC in India or in the UK picking this up and looking, well, it's just another outage, I'll quickly balance this here. That's different to saying, I know this is power. My schedule says it's going to be out for 8 hours. It's going to hit a peak time over here. I may want to rebalance this traffic in a very, very different way.
Mm-hmm.
And that makes this really important, that I do have a way in the network to pick these things up, etc., and then make decisions on that that aren't necessarily related to some guy's impression in India who just saw that the router went down. You know, so there are a lot of possibilities here to get pretty interesting with how you do this. The other thing is, if I've got algorithms that are learning how to balance traffic when something is down, I can tell that algorithm, this is because of power outage, learn something different, versus this thing has just rebooted itself and may come back at any instance. So there are a lot of possibilities I see here, and yeah, I am extremely interested in this.
Thanks, Andrew. Yeah, I think when it comes to the what's in scope and what's out of scope, if people do think this is a problem, we need to balance. I personally don't think we should get too caught up in how do we create schedules. I think that's kind of beyond the scope of what's achievable in a reasonable working group schedule. There is some really cool stuff we can do once we have a schedule, and I'm going to get onto this later, but it's more about trying to keep that scope down. But that doesn't mean other things can't be built that we consider to be particularly out of the scope of something like a routing working group. But yeah, once you've got this data and you can work out how to get it around your network and get it in the system, there's a lot of cool stuff we could do with this, I think. Sorry, Karen.
Yeah, Doug Cross and Huawei. I asked the question on the chat, and I thought I might relay this here. It's called time variant routing, but I feel there are different variances we may want to consider. It came out already before. It may well be energy. It may well be locality. You know, I find time variant, the focus on a schedule very limiting, if you will. And it sounds, you know, link is up and down, schedules, I put a schedule into the router, you're done. But if you have dynamic conditions that may be predictable as well, upon which you actually want to change your routing, I think this, you know, creates a much richer space for probably very, very innovative solutions, if you will. I
take your point. I'm really trying to stop boiling oceans here. And I do wonder that I don't want to disappear down to a generic expression evaluation condition causes effect That's programming in the network. I think that's still very much the work of the IRTF. I think if we say things change at a point in time, can we prepare ourselves in advance? That reduces our scope to something achievable, which will have noticeable benefit. I'm not saying everything you haven't said is not really cool stuff and would be great to do. I just don't think it's achievable, particularly within one BOF from an administration perspective, not from an intelligence or an ambition perspective.
Thanks, fair point.
And just for clarification, I believe it either comes up later or you said it earlier, that at the time change, other parameters may change, like bandwidth and latency. and
Yeah,
loss.
so a scheduled change in energy consumption. I think we've got use cases talking about that. In fact, I know we've got use cases coming talking about that. It's not just on and off. It could be, we know that I don't know, the atmospherics are such that our satellite links are really good until there's a rainstorm coming in at 3 p.m. this afternoon.
You can do a lot with the schedule. I do agree. I mean, if you provide an API in the schedule building, that's how we solved some of the problems in the past. But obviously, the conditions for the schedule can be exactly along the dimension that I just mentioned. It could be driven by energy prices in order to do carbon-aware routing. It could be based on expected movements. I think on the mailing list I sent a paper around, we published 20 odd years ago on using contextual information. I walk down the house, we walk to the left, I walk to the right. You can boil this down into a schedule. If there was a proper API into the schedule making, then you can probably go down the route that I'm suggesting.
I completely agree. And I think the carve point here should be, let's say we have a schedule. Let's see if we can define what that schedule should have inside it. And let's discuss the kind, and I'm getting beyond the problem statement into what I think the scoping is. So actually, I'm going to stop. Can we revisit this in my next slide or my later slide deck?
And last question.
Stuart Bryant. So when a node or a link changes, the network transients, and during that transient, a lot of innocent traffic is disrupted because of the formation of microloops. So we're going to do this. Can we include in the base technology microloop prevention in some way or other to try and minimize this this very disruptive effect? The technologies for doing it are well known.
Absolutely. I see no reason why that shouldn't be considered. That's just the sort of thing that we can attempt to avoid. If we knew it was coming up, we might be able to use different techniques to say, when we have to make this change, because it is predicted, we can avoid that sort of microloop formation or whatever, because we can all, we being a set of routers or whatever, we can pre-agree an alternate topology to have prepped without those microloops, and we can pre-agree to make.
No, it's not quite as simple as that, right?
Oh,
so
sure
because you have to deal with the lack of synchronicity in the changing in the fibs, which can take quite a long time. So actually, it's not an instant event changing the topology, but actually a topology change process that you need to do that takes you from the old topology to the new topology via a number of short-term virtual topologies usually.
And that sounds absolutely like something that should be addressed as part of a TVR working group. I think that would be absolutely a charter item to say, can we in general terms describe how one makes this change such that we avoid these things? And the reason I say general terms is I don't think it's right that a potential TVR working group should tell link state routing what to change in OSPF. We should go to OSPF and say, these are mechanisms that we talk about. Can you integrate it?
The techniques were investigated quite some years ago now in the routing area working group. So a lot of the techniques are already documented.
Great, let's have them. Let's use them.
Perfect. Thank you all for a really good discussion, and hopefully we have a good picture of what the problem is we're trying to solve here. That said, we're going to look at some specific use cases, and I think they'll echo some of the conversation. Ed.
Oh, hi, my name is Ed, and Rick is taller than me. So let's see. Okay, so when Rick and I started talking about what would time variant routing look like? Obviously, a problem statement was good, but everyone has in their mind a mental model or a problem that they've encountered and that they're trying to solve. And trying to bring that down into a series of use cases was an interesting endeavor, because we could have 2 of them or we could have 2,000 of them. And how do we scope and understand what differences are important to talk about? So what I want to talk about for the next 10 or 15 minutes or so is an initial take of how we carve out use cases to identify what we think are the unique differences that and the expected benefits in those use cases of something like TVR, or time varying information. Next slide. So to do that, I wanted to just go over some background, the approach that I took in laying some of these out based on the conversations in the on the mailing list. Talk a little bit about some formatting, and then go over what I call sort of the 3 use cases, which are kind of categories. And I'll name them here, and we'll go into them in detail in just a moment. The first is cases where nodes change their functionality to preserve local resources. Local resources like resources local to that node. It's battery power, thermal environment, local storage, where preserving that is more important than some other node functions. Another set of use cases are cases where a node wants to adapt to changing external conditions. Power is really expensive right now. Data is really expensive right now. It's not a matter of node survival, but it's a matter of reacting and working better in an external environment. And then the last one, which is one that is probably very familiar when we talk about things that change over time, is what happens when nodes in our network are moving. When they're moving far away from each other, or when they're moving through a difficult environment, or when one just turns a little bit and can't talk to the other. So next slide. So before we go into those 3, how did we get to those 3, and how are we going to talk about them? So how did we get to them? Well, obviously we wanted to constrain anything we talked about to the problem statement that Rick had just talked through, because this is the problem that we are trying to solve. But then when we talk about use cases, it is categories of these problems. So we say use cases, but the 3 things that I just said, I believe, are categories of problems or characteristics of problems. And the idea here is that, again, I don't want to worry too much about 2 or 3 or 4 instances of the same kind of problem and calling them different. Another way of saying it is, what we think here are, from a use case perspective, these 3 are such that a solution for one exemplar of that use case could be a solution for any other exemplar within that use case. So the format for this is, we want to define what they are. We want to list out what the assumptions are. And assumptions here, because the use cases are, again, a little bit abstract, are what information do we think would need to be present in order to yield deterministic benefits from having a predictable schedule. And then the next part is, okay, well, assuming that we have data that we need to key off of, then what are those benefits? And when we list out those benefits, it's not, and there will be a list, typically 2 or 3 or 4 or 5. It's not that we think we will get all of them all at once all the time, but maybe you get some combination of them and in different cases. And then last, I'll end each use case with a quick exemplar just to try and ground the thinking. But then afterwards, we have 2 more presentations following this one that will go into deeper detail on some more specific exemplars. Next slide.
And we probably will wait for discussion until all 3 presentations go. If you do have something that's just like a clarifying question, that's great. But for discussion, let's hold it until the end of the 3 use cases. Thank you.
I will happily defer discussions until I'm not on stage. Right. So use case number 1, local resource preservation. I mean, this is the idea where we have nodes that just operate with limited resources, either because they're in a very difficult environment or because there is some nature of the node itself where it is meant to be small, it is meant to not need a lot of power, it's meant to not have a lot of storage. Typically smaller things may be more susceptible to thermal changes. And more importantly, the management of local resources is going to dictate the function of the node. So cases where we have nodes that will pause non-critical events to allow the node to stay alive and on battery life longer, to extend the life of the node. Or if we know that something interesting is coming up, and so we want to power things down so that when that interesting thing happens, we will then be able to do data collection, data exfiltration, or if we have to go into a thermal safe mode, or more interestingly, if we do have a relatively small amount of storage and that storage is filling up, maybe that is the time and the predicted time when storage may fill up, when it's time to turn on things like radios and start transmitting again. And then, of course, the possible benefits of this are that if we understand a little bit about the future, particularly as it relates to when links may be going up and down, we can do a better job of our own resource management. Next slide. So for this and the other two use cases, there are sort of two columns here. Again, the assumptions, which are on the left, say the better we know these things, then to the right, the possible TVR benefits, the better we would be able to achieve these other things. So if we assume that we are a resource constrained node, and if we assume that that resource management is important and in this category of use cases is sort of dominant to node function, then what we would say is it's important in these cases to know that our resource expenditures are knowable. The amount of resources consumed by node functions can be known in advance. If I'm managing my node functions based on the amount of battery life left, and I know I have to transmit a data volume, I probably should know how much power it is going to take, or average, to transmit that if I'm making decisions based off these things. So we assume that that's calculable on the node, or knowable on the node. And then the next piece of that is we assume that the accumulation back of resources, again, using the example of power, how much we tend to expect to get back of battery charge from things like solar charging, when will that get us back to good, should also be calculable. And then the last is that if we're making node function decisions based on the resources at a node, there is an assumption that that set of decisions and those rubrics or those metrics aren't changing so rapidly that within any sort of given period of time, we're not changing our internal cost functions. Because if you're always looking at a different way of managing resources every few minutes or every few hours throughout the day, it becomes more difficult to get deterministic benefits back from adhering to something like a schedule. However, if you have those kinds of knowledge, and we believe for nodes in these situations, they do understand these things because that is their resource management job, then you get better power savings, you can get better thermal savings, you can get better storage management, and really honestly, just the data delivery, because that's what most of this is about, continues to be a little bit better, because if you can manage your resources better, if you can stay active in the network better, if you're not wasting power by having a radio on when you don't think there's a likelihood of having a link, for example, then you're able to eventually get more data through your system. Next slide. So a graphic on here is to come back and say, and these are taken from the use case documents, which are published as well. If we were to look at a very contrived example of, say, a 3-node network, node 1, node 2, node 3, and we were to put a very simple plot that says with power on the vertical and time on the horizontal, that a node would choose to keep a radio off until such time as it accumulated enough power to want to transmit something or listen for something. Then you could put some very different plots together for nodes that maybe are distributed in a particular way, and you could see how that would change underneath of that, the topology of the network at different times, time 1, time 2, and time 3. So this is something that's, while generic, I think we can all come up with or understand how this would look in actual deployments. From an assumptions perspective, we think these power graphs are knowable, both accumulation and expense. The resource, the radio management, that sort of horizontal line of how much or how little isn't changing over time. And it looks at places here where the topology itself is predictable, schedulable, and likely also communicable across other nodes in the network. All right. Use case 2, which is now not about resource management and preserving node function, is instead about adapting to external conditions. And the idea behind this is that there is likely some costs, some external costs associated with participating in a network. And a common example of that is use of infrastructure, use of power infrastructure, use of data infrastructure. Nodes that are wireless, they will, for example, use cellular infrastructure. I think all of us understand the idea of on-peak and off-peak usage times and what happens with overage rates if you go over your on-peak minutes. It came out in the news, 3 or 4 days ago, that Starlink has come back and said, if you go over a particular cap, then that will be problematic and you will have an overage. However, our off-peak time is, 11 p.m. to 7 a.m., I guess your time. And so that means, great, if I have, low priority data, then that's when I should choose to send it. So if we look at that and say, if you're looking at the cost of electricity, if you're looking at the cost of data rate, if you're looking at things that are changing in the external environment, but the overall total cost of operation of the node, then that is additional predictable, schedulable information that may impact how you want to make routing decisions or just generally handle your data. Not all the costs are strictly financial, and the benefits here may be that we choose to rank or associate cost functions with the use of links in a different way with the extra information. Next slide. So again, assumptions and benefits. We would assume that if this were something that would benefit from TVR schedule-like information, we would say we can measure those external costs. We understand our data rate usage or our energy usage. The changes in those costs are either predictable or scheduled because they were predicted, and that the cost differences persist for long enough, and optimizing them has a savings that is big enough to justify the extra computation or work to figure out and make use of this additional knowledge. But of course, I think if you do that, then you could come back with some benefits and say, well, wait a minute, we can filter links. This link was very low cost 5 minutes ago, but now we're in on-peak hours where we're about to go into overage, and now this link might have a different higher cost, either financial cost or logical cost, and maybe we want to think about it differently because of that. We can also come back and say in certain cases, maybe we want to plan and accumulate data before we use a link based on its cost. Maybe we even want to look at the fact that if a link is high rate, but we think that the good put might be relatively low versus the throughput. If anyone's ever looked at nodes who spent a lot of energy trying to punch an RF signal through a storm, for example, maybe we wait on that. For a variety of reasons. And again, all of this comes back to trying to get better data delivery and make better data delivery decisions. Next slide. Again, from this one, a contrived node 1, node 2, node 3, where we come back and say, if we were to simply on the vertical say cost high low time T1, T2, T3 across a 3-node network, those can change over time. In this case, maybe it's spatially distributed nodes with a cellular backhaul. And we look at how the topology does not change. The links are still there, but we may come back with things like, well, node 1 to node 2 can be either low cost or high cost at different times. And even perhaps in this third case at the bottom, you may wind up saying, if I want it to be low from node 1 to node 2 and low from node 2 to node 3, and it's something that's reasonable in your network, you may actually hold on to it for a little while, waiting for that node 2 to node 3 cost to be lower. Next slide. Then the last slide is sort of these mobile networks. And obviously, LEO Satcom is an example of that, but there are others. And there are really 3 cases of mobility, but again, under the idea of a solution for one might be a solution for many. So we don't necessarily perhaps see them as 3 distinct use cases. Are cases where I have 2 nodes have moved far enough apart that they lose the ability to talk to each other. Or 2 nodes have not moved too far apart, but they together are moving through an environment, or an environment is moving through them such that they can't talk to each other. Or one of them has pointed their antenna somewhere else and they can no longer talk to each other. All of those are mobility-based or motion-based losses to a link. Next slide. So again, from an assumptions and benefits point of view, if you understand the motion, if you know where things are going with some predictability, with LEO, we tend to know where they are, but we maybe don't know what's powered on or where things are pointed. Or if you understand the environment, which may be also impacting you, then that is knowledge you can exploit to understand when an adjacency would go away, understand when a link could come back, maybe to even include that the resumption might be a different link than the one that went down, which would be a useful thing. That you can understand how your data rates would be adjusted, and generally you can use all of this for better filtering of the links as well. Last slide. So again, in our networked LEO constellation, if we have a couple of spacecraft and we assume that they have a different ground coverage over time, for example, spacecraft 1 is over ground at time 3, spacecraft 2 at time 2, and so on, then we can sort of understand as this train goes by over the ground station in minutes, we need to understand handoff, and we need to understand that certain links are going up and down. And as one spacecraft leaves the ground, you then need to go, for example, to an inter-satellite link to the spacecraft behind you so that it can keep that going back down to the ground. And that's something you do because you can predict and you have a schedule to deal with that level of dynamic topology. So that's 15 minutes on some high-level categories of use cases that we think would benefit from TVR. And then I think after this, we have a couple of deep dives into more specific examples. Sure.
Thank you. Sorry, I turned the mic off. Kevin is going to present next, and he is remote. Kevin, you don't need to share your screen. We'll just pass you control. So just hold on one moment. And if you can pass him control. Kevin, can you say something to make sure we know you're here? Kevin, you may have to unmute your mic. Oh, here we go. Wrong Kevin. Short. But Kevin, we don't hear you. Dan, will you? No, different Kevin. That's fall. We're looking for short, or did I say that backwards?
Kevin just mentioned in chat that he doesn't have access.
We need audio. He needs audio. Don't worry about the slides. Just get your audio working. And Dan, if you would come up to be prepared to present just in case. Short, yeah. Kevin, you need to unmute. We can see that you're muted. I think maybe Dan, if you would take over, and then if we get, Kevin, if you get your mic issue sorted, you can just start talking and we'll let you run.
Cool. So while we figure out the audio and some slides, my name's Dan. With Kevin at Airbus, I'm at Lancaster University. We are introducing a use case. Next slide, please. There's already been a couple of mentions to sort of emerging satellite constellations, the space-based use case. It sounds extremely futuristic, but of course, these networks are being put in space. There are several large constellations with tens, hundreds, thousands of nodes whizzing around the planet at the moment. They are extremely small. They're increasing in size and number. They have multiple link types. Next slide, please. That we can choose in order to set up the physical connectivity. So in some of the constellations, there are high bandwidth interfaces on the order of gigabits per second using free space optics, operating actually at speeds that are significantly faster than traditional sort of Earth-based, fiber-based systems. There are also radio interfaces, and those RF interfaces are also evolving over time up to sort of gigabits and tens of gigabits per second. In terms of building the space topology, we can continue through various space segments using interspace links, ISLs, but we also have the opportunity with some constellations to bounce down to the planet using base stations. And in sort of several major countries, there are often multiple base stations that can be used. Next slide, please. So what we need to kind of figure out is how we build this network topology, given that there are several space-based segments that we can use, as well as sort of dropping down back to terra firma. We know that these links offer different characteristics. So there are bandwidths, latencies, potentially jitter as well. If you're a Starlink user, and I am, as well as a tester, you'll notice that we have a lot of bandwidth and availability, but actually there are queue issues, and latency and unpredictability for jitter can cause a major problem for certain low latency applications. Next slide, please. So we need to figure out in advance how we're going to build our physical topology, given that there are multiple links, bandwidth constraints, potential queue issues, and also the amount of power available on some of these satellite nodes, as well as, of course, the bandwidth that's going to be potentially available at a given point in time. Now, this is a network path computation problem that can be solved with a combination of traditional techniques. We heard earlier sort of some linear solutions like Dijkstra. You could, of course, use a control center with humans, sort of biological path computation to do some offline planning to try to optimize your network. What we're looking for, next slide, please, is potentially a method, a process of building a network topology virtually in advance that can then be overlaid. So we also need to consider that this isn't just a planning problem, but it needs to react potentially to changing real-time conditions. But real-time is relative. So real-time for a fixed network might be a few seconds or tens of seconds when you start losing an adjacency to a particular sort of next hop neighbor in your IGP. But in space, sort of a real-time change might be over several hours as you're recharging a particular node in order to sort of gain power and then be able to light some new interface. There will also be connectivity potentially coming online predicted, though that is not space-based, but is high altitude. So there are sort of UAV, unmanned aerial vehicles that potentially can augment your network. Next slide, please. So we will need to build this kind of network graph, including some sort of online capability with the ability to consider offline. And maybe the definition of online and offline needs to be clear here for people. Essentially, it's some kind of entity that is talking directly to the network. I suppose that's what I might consider online. Offline would be to pull out a traffic engineering database, run some evaluations, create a candidate topology. That might be done in an offline instance, and then I want to apply that at some point in the future. But something has to kind of merge these two databases at some point. And if we had Kevin online, he would probably talk about ConOps, which is a form of sort of operational management that's done by a team of people augmented by heuristics or sort of non-heuristic technology. So I suppose for some of these use cases, the time horizon is very different. You know, for a satellite network, we might be talking about minutes, hours, days. During the chat, someone was talking about deep space connectivity as well. For other use cases, it might all be happening over several minutes or hours. And I know that we get excited, or I get excited about space-based communication, but the same concepts and requirements also apply to things like rural internet, where essentially you've got microwave links or indeed free space optics, where you've only got these links available at particular times of day because that's when you can get enough sunlight to power the interfaces as well. But they're highly predictable because generally the sun will rise and set in the same location. If it doesn't, then we're probably in trouble. Next slide, please. And the network discovery, building the topology, analyzing the topology, making the predictions, building some future candidate technology. And I mentioned in the chat that this feels like or sounds like potentially a scheduled virtual network topology. Needs to apply to a variety of service types, users that are actually attaching to the network. And those are listed there for sort of space-based, marine, high altitude, unmanned aircraft. Next slide, please. So what would we like from TVR? And of course, this is sort of walking into a toy shop and saying, well, Dan, choose anything that you want. I'm going to try and grab everything I can, knowing that there is a kind of reality question that we need to apply here, and wanting to kind of minimize potentially the amount of state that gets created and potentially injected in a routing protocol that's going to be used in an online function. So bear with me. We've just kind of, Kevin and I have put everything potentially that we would like here, but there has to be a method of exporting or retrieving information from the network, discovering capability, understanding what metrics we will need to consider. And it's all of the standard sort of routing metrics that we might want in terms of latency, bandwidth, etc., cost. But cost might also have a physical element to it in this case. So there'll be a network cost and maybe a physical cost of powering a unit versus choosing a particular link. We will need to consider the sort of the resiliency here as well. There's a restoration consideration. Not only does the generation of a virtual network topology or some candidate / future topology need to be considered, but it needs to potentially react to changing network conditions in the event of some kind of catastrophic failure, such as the removal of a node or degradation of a link. We may need to switch over. And that could be, I think someone mentioned earlier, occlusion, which may be weather or some other sort of debris that's getting in the way. Okay. So I'm just looking at the time here as well. So maybe I'll stop because there are going to be commonalities with some of these requirements across the other use cases. Are we taking questions now, or are we saving them for after the
I would prefer to save them, but if you have a clarifying question, please come on up or come to the queue. And Eve, if you get ready for the next one. Thank you. I think we're going to have some good discussion on the gaps and mechanisms, so I want to make sure to reserve some time for that. All right, Eve?
Okay. Can you hear me?
Yes, you sound good. Thank you.
Terrific. Okay, so I will extend this conversation by talking about something we've begun to call carbon-aware networking, which we believe solidly falls within this discussion around time-variant routing as an example of an environmental impact use case. And I will tie it to one of the use case categories that Ed so clearly talked about. Next slide.
You have control, Eve.
Oh, I have control. I do? I don't think I do. Oh, I see. Okay, here we go. I do have control. All right, so the backdrop here is that for anyone who's been following the UN Intergovernmental Panel on Climate Change, there's pretty dire urgency to try to meet these thresholds that are out there, after which, we really can't even model what the consequences are going to be. And in the most recent reports, those recommendations and reports have been called, code red moments. We're really at a tipping point. And so what can all of us be doing to be more considerate about climate change and greenhouse gas emissions? And if you look at the information communication technologies contribution to those emissions, It's fairly sizable and growing. And some estimates are that at least the electricity usage by ICT will be between 2 and it's about 2% now, but by 2030 will be about 6% of all global electricity, which in turn has a carbon footprint. Although data centers get all of the attention in terms of their footprint, the network impact rivals that of the data center. And in some estimates from the ITU, which typically makes these reports and publications on a regular basis, the network is at least as large and sometimes as large as 1.5 times the size of the data center in terms of its footprint, carbon footprint. There's also the recognition that there is an increasing tidal wave of data that gets generated by all the things that are connected to the network. And it's almost as though the only way we could get to a situation where we have carbon neutrality or net zero impact is to not just consider energy efficiency of our products and components, but to really think about the coupling of renewables with all of our infrastructure. And additionally, when you think about what is so disruptive about this is that if we're going to be moving to clean energy to address the issues of greenhouse gases, I'm hearing an echo. I don't know if others are hearing an echo.
We're not, sorry.
Oh, okay. To move to the electrification of transportation, hopefully clean electrification of transportation, we're going to need about 4 times the amount of electricity that's currently being generated. And some estimates are that that's going to entail about 20 times as much infrastructure that's already out there. So we're at this very interesting moment. We know that there's going to be a long arc of rollout of this infrastructure. And so in that time, and we may never get to a fully renewable or clean energy oriented grid. And even if we could, there was going to be this long arc of infrastructure rollout, even longer amounts of time than how long it takes to roll out telecom or internet infrastructure. And in that time, we want to be thinking about, well, how can we steer our usage of electricity to be the least impactful? And there is this metric that is quite interesting, which is carbon intensity, which is a measure effectively of how green is the electricity. And we've been talking, Rick and I and other colleagues at Yale University and Oxford, about the what ifs behind, could we add to the performance metrics of networks, which are typically described in terms of their packet loss, their latency, and their jitter. What about if we could describe the performance of the network in terms of not just its energy usage, but also the greenness of that energy? And carbon intensity is better when it is lower. And so if you were to think about sort of sustainable networks, you'd want to be thinking about how do you design them so that they consume less energy? How do you decarbonize the electricity that they do consume? And then there are other kinds of actual environmental impacts that we're not going to get into today, that are other concerns, that are things like around water and waste and chemistry and things like that. Now, we're inspired here because many of the hyperscalers are adopting techniques that they are referring to as carbon aware or carbon intelligent computing, where they are physically time and space shifting their workloads so that we place them in places where there is the least carbon intensity. And the attempt here is, as stated earlier, is to maximize the usage of renewables like solar and wind alongside of other things that are considered clean energy when we look at them from a greenhouse gas emission or carbon standpoint. There's also another interesting phenomenon happening that if you look at places like California and Germany, parts of the globe where renewables are being integrated at an accelerated pace, and consume or at least deliver a high percentage of the electricity in the grid, unfortunately, there's a mismatch between the supply and the demand for that electricity. And so sometimes there's excess renewables being generated and that go wasted as a consequence. And so what the data center community has begun to do is to use the data centers themselves as a virtual battery of sorts, so that in moments where there is an excess of renewables, that time elastic workloads are sort of on the ready to absorb that excess energy. So naturally, the question is, well, how does this relate back to what we could be doing with networking? And we do believe that there are carbon-aware techniques that we should consider adopting. And that when we started to look at this problem, we naturally thought, oh, well, clearly we want to take routes and we want to route our data transmissions through parts of the network where there's the greatest carbon efficiency, so where the carbon intensity would be lowest. But there's also DTN-like time shifting that we could also leverage here. Several of us who are part of this conversation also come out of the deterministic networking community. And there is the ambition that for this kind of traffic engineering, we'd like to also be able to guarantee that we stay below certain thresholds along pathways in the networks, and even go so far as to ponder, could we be reserving resources, whether those are battery-related resources or predicted availability of renewables along those paths. In the same way that, for example, in the DetNet community, we talk about, or at least in the time-sensitive networking community, we talk about reserving buffers along pathways in order that our packets don't confront any kind of congestion along those paths. So that's the equivalence there. And then finally, in order to do some of this, we really do need telemetry, and how do we make that telemetry itself as a workload be carbon aware? So I was inspired by Ed's slides, and so I took his example of, sort of providing this overview of, I believe that the carbon-aware networking falls squarely in the operating efficiency use case, and that we could comprehend carbon intensity as part of a cost function for links. The reality that we have batteries in many situations, not just virtual batteries, but actual batteries, also means that there's shades of use case one about resource preservation that we could leverage, because it may be the case that you might want to opt for battery operation when the battery has a mix of electricity whose carbon intensity is less than the carbon intensity coming out of the wall socket. And something I won't really get into because I really haven't thought about it really deeply enough, but there is this possible shade of use case 3 about mobile devices, that we can dispatch mobile distributed energy resources, whether those are energy generation or storage, in the places where they're needed. And this is something that commonly occurs in the event of emergencies, for example. But how it relates back to TVR is we recognize that there are causes for the loss or reappearance of adjacent links that are related to external environmental factors, such as the sun is shining or the wind is blowing, or these thresholds that we've talked about. Either those have been exceeded or we're staying beneath them for carbon intensity. And clearly there are benefits because the expected loss of links are not seen as errors, but as optimizations, and that the resumption of these links is not about the rediscovery from scratch, but they are waiting on standby. This is, of course, I went back to Ed's slide, unfortunately a slightly earlier version of Ed's slide, but the point is that it is really to ask the question whether this use case meets these assumptions. And I think to a large degree it does. We believe that there's measurability, that there's predictability in scheduling when these cost changes occur, and we can communicate that in advance. And that, here's something to consider is how often are these changes to the topology? That is in part a function of how often something like carbon intensity is shared by the utilities. And we can come back to that in a moment. But there's also the question about, is the cost of the savings, does it justify the effort or the work that we're going to do to enable this? One data point is that in the recent California temperature, during the summer in California, we had a spate of temperature and weather that the utilities, reached out to the populace and said, could you please not use your electricity? And someone turned around and did a model, given the amount of electric vehicles that we have and the battery availability, could we avert blackouts and the cost of that to to the economy. And so something like that might be a way to quantify, is what we're doing beneficial enough? I think it's hard to specify completely what's enough, but we can also come back to that. But in terms of the possible benefits, I think that it also matches up quite nicely. I don't believe that it has this property about burst planning. One interesting facet in terms of the environmental measures is we are going to face some regulatory pressure. So again, there's going to be some carbon taxes. And so some of this may be around, are there actual costs, financial costs that can be associated with this problem that also are part of the link state, not just environmental. As I intimated, carbon intensity is not something that network operators own. It's really the utilities own this. And there are issues about how granular the areas or regions are within which carbon intensity is derived and actually exported and shared, the frequency with which it's updated, and what parts of the world it is actually being openly communicated to beyond just the utilities. There's this subtle interplay between the batteries and the electricity generation that we'll have to deal with. And as I intimated, the justification of function is something that needs deeper analysis. I think that is it. There are a few other resources if you'd like to read more about sort of the whole state of carbon responsive computing and towards carbon aware networking. And I think we are now, we can open up the mic for all three presentations.
Yes, we have about 7 minutes or so for discussion on this topic. We're going to reserve time for discussion.
We can't hear you. I think you had turned off the mic because of the echo.
Abba Salam? Can you hear me?
Yes.
I can, but you're very quiet.
Okay, Abba Salam, please
Yes.
go ahead.
Yes, thank you very much. I think this working group is interesting, and I'm willing to help in working in this group. But I still see that the solution or the proposed solution is not clear. From the beginning or the first presentation, it considers only or saying that it's varying the metrics or changing the metrics for the routing protocol. It's not much clear. I think maybe I can propose that either we say that changing or a scheduling change or some kind of algorithm, are we changing the algorithm or only the metrics? At least we be clear on that also, because, and also we need to be clear on the conditions, or that we can say initial conditions for this kind of variation. And also we should consider the stability of the routing mechanism. So that's my comment, and thank you very much.
Thanks. I think that in the long term, what we'd like to do here is to define models and stuff. Of course, it's up for the work group to decide what the actual scope is, but to figure out what the models are and what needs to be done and kind of push it back to the routing area, the specific routing protocols to figure out how to represent those things and how to deal with them. Although there may be offline components, as Tony has said in the chat, and other things that we need to deal with. But I think that, we're trying to just get to the point where we have a good solid set of use cases before we deal with solutions. So.
Dejan Bogdanovic. So this topic is starting to show up in the IETF for the last few meetings now. And it's a big multidimensional problem. I'm not sure that the IETF as a community is the best community to deal with all those, because we don't have the expertise in some of those dimensions. But maybe putting that into the IRTF, I think it would be a much better place to deal with that until the problem has been defined at the technical level, what we could go down and solve. Being like much more specific.
Ms. Luberger speaking as contributor, I completely agree. There's a lot of issues here, and one of the challenges for the routing area is going to be, what does the routing area do? I think and there was a side meeting from the transport area yesterday, is from the transport area, they're going to have a question of what do they do? So it may not just be one working group, but it may be multiple, because as you said, it's a really big problem.
It's a really big problem. You have to define the policy and how to enforce that policy over the network. But what is the policy that you want to enforce on the network?
Dan?
Daniel King. So with the greatest respect, I have to disagree with Dean. It wasn't actually my intention for coming up here, but I don't see this as an IRTF problem. I see this as an engineering problem, and I see this being applied to existing infrastructure that's out being used commercially. So that's just my thoughts there. The point for coming to the mic was, thank you, Eve, for your presentation. I see some sort of commonality in terms of requirements for the area, the use cases that you mentioned there. We've got an internet draft. It's actually in I think the routing area. So I wonder if we can work offline to kind of sync some of our requirements and figure out the best way to kind of publish that. I suppose some of that may be dependent on the conclusions that we reach at the end of the session today as well. Thank you.
Mallory?
Okay.
Hi, Mallory Nodal, Center for Democracy and Technology. I just wanted to support this work and thank you, Eve, for your presentation. I'm also agreeing with others in saying that I think these topics have to be mainstreamed in a lot of the IETF, and we shouldn't imagine that they should only happen in one place. So that this work is happening here makes a lot of sense. I did want to also point out that in the IRTF, we at least had one recent presentation, although we've had some in the past, from Bharath Raghavan, who came to talk about the ways to reduce the footprint. So I think some of the metrics that are given around, how much electricity is needed and so on, I mean, it doesn't really address the fact that sometimes the source of that electricity is also potentially a problem. And so accounting for that, I think there just needs to be a general approach to reduction and minimization, because that's probably the best direction of travel. So, but thanks again.
Thank you. Lars?
Hi, Lars Eggert. So since we're going down the scoping discussion role, I want to suggest a principle that we might use to scope or to narrow the scope and maybe see if that sort of has some agreement or not. So I heard the Manet use case being brought up. So in my mind, right, so in the internet, we run routing and then we run transport on top, and transport basically operates on RTT timescales. And if routing also starts to operate on RTT timescales, we actually don't really have a transport thing that we know of that will operate on top of that. So I wonder if we could limit this proposed work to the space where changes to the topology happen on, timescales that are a factor X for some number of the 90 percentile RTT or something like that. So it's there's a certain expectation that the topology isn't crazily changing all the time, right? It's generally stable, and maybe you can predict when a change will happen. And so you can, when you have a path, you can run a TCP style transport over it. I think that might sort of get us in a box where we might know what to do about for standardization. Thank you.
Yeah, that's a helpful comment. Joel Halpern made a similar comment in the chat that, are we talking minutes, microseconds, nanoseconds? And, the general discussion there is we're talking longer periods and scheduled items that are maybe minutes, hours, longer, depending on where you are. So that's a helpful comment. With that, we're going to move on to Rick. He's actually going to be the last sort of formal presentation. And we've reserved an extra 10 minutes. We had more when we started, but we reserved an extra 10 minutes of discussion. And it's probably best just to integrate it into his talk and to the later slides. Rick, over to you.
Thanks, Lou, for saying formal. I rarely do anything particularly formal. So yeah, this is almost a continuation of where I started, and I hope addresses Lars' point directly, and I think I'll try and make comment to Dean as well while we go through. So Dan, while we go through this. Next slide, please. So I started, this kind of goes back to where I started with my thinking and my discussions with Ed and various others about this too. I believe there's a kind of a spectrum of routing environments, which goes from the very fixed, never change, doesn't actually exist, environments where we're talking about ISP backbones, cloud service providers, that kind of stuff. It's big, it's stable, it's manageable. It's expected, when you put a link in, somebody's actually laid down something physical and plugged it into something else physical. You expect it to still be there. And at the other end of the spectrum, you've got swarms of UAVs buzzing around in an uncontrolled environment in the middle of a thunderstorm in a war zone. That world's worst ad hoc, everything is in complete chaos, contested environment. But those aren't just two use cases. That I believe there's a spectrum. And I just want to kind of look at the two extremes of that and introduce the idea that I think there's either a second dimension to this, or there's another environment where I think TVR lives. So next slide, please. So really, if we look at the fixed environments, there's some general assumptions, which is nodes don't move around. If you put something somewhere, it's going to stay there. Things have a well-known connectivity to their peers. Yeah, the links to the peers may fail, but the peer on the other end of that link is going to be the same peer it was when you started, because that's how you configured it, or your auto configuration system kind of found it and found it was there. And link service is maintained by reactive rerouting, and the key point is it's rerouting. So something fails, we'll go round the problem and we will maintain those end-to-end paths, but we will react to that failure. And this ties back to what I was saying at the beginning. And the fourth point is links are expected to come back. So there's active monitoring to say, is it back yet? Is it back yet? Or, and yes, there are more advanced techniques around that, but fundamentally when your link fails in these fixed environments, the expectation is it should be there. So let's try and work out when it comes back so that we can reactively reroute to it when we spot it come back nice and promptly and get back to that stable thing that the sysadmin wanted to happen. And it's kind of the mindset that has influenced the design of those protocols. And you could say it goes back to the early days of ARPANET and academic networks, where people built it in a lab and you knew box 1, 2, and 3 because you put them there and plugged them in. It was kind of that mindset behind it. And yeah, we have a much more mature ops derived view of these things and say, yeah, things do fail, things do get swapped out, things do get upgraded. But that general assumption about stability permeates the thinking of the routing protocols in that area. And without I'm not trying to say any of these things are bad. I think they're fantastic by their persistence and longevity. You know, we're talking BGP and OSPF and ISIS, and even I'll point the finger at BFD here to say it's a great technique for getting prompt recovery, but you are reacting to a failure and trying to recover quickly, and BFD helps you do that. So the key issues, and I kind of touched on this earlier, but I'll repeat, is that when you're reactively rerouting, you will always have loss, even when you knew it was about to happen, because you are reacting to something happening and going, oh, God, it's gone, right, oh, we'll go this way, it's fine, or luckily, you know, there is still that loss while you switch. There an opportunity to do something seamless because you knew it was coming is missed. And the other side of it is that proactive monitoring piece. If you know it's not there and it's not going to be there until tomorrow, why are you monitoring to see if it comes back yet? And it's just a bit wasteful. And going back to some of the use cases that Ed and Eve and Kevin, it is Kevin, isn't it? Yeah, that Kevin presented and Daniel presented. Some of those environments, resources are really important. Some of those environments, the fact that we're even burning these resources is important in a larger sort of global scale. And I'm a computer scientist. I don't like wasting compute. You know, why have I got an inefficient algorithm doing something? Let's just be purist about this. So there's lots of reasons from different aspects about wasting resources is not a good thing. Let's go to the other end of the spectrum. So next slide, let's look at MANE. And this kind of comes back to Lars's point, where there are environments where everything is wild. So nodes move randomly within the topology because they may be physically moving, they may be doing crazy things at the link layer, which causes all sorts of stuff to go on. Links are frequently break. That's a general assumption in the world of mobile ad hoc networking. Your links, they're not going to be stable. They are pretty much, you know, as I say, links are considered ephemeral, effectively. So your network service, just like the fixed environments, it's maintained by reactive rerouting. I found a new opportunity, I've lost an opportunity, I'll quickly rebuild my topology. I may do it in very exciting and funky ways because MANE tackles this environment that may be considerably less efficient than link state routing, but it will work in environments where link state just doesn't. But it's still fundamentally reactive rerouting. You are reacting to some break in your current assumption about your end-to-end path, and you are therefore desperately trying to work out some alternate way to reestablish it. And links, as I said, are considered ephemeral, and therefore adjacencies are proactively discovered. So you'll see if you do read through most of the MANE protocols, instead of understanding that the peer on the other end of that link is expected to be there, and let's try and keep that establishment going, BFD style, or you know, however you want to do it, your TCP keep alives, etc. You'll see a lot of the MANE protocols will do things like active discovery of, oh, are there new peers? Are the peers I was expecting still there? Have any peers disappeared since I last did? There's a lot of helloing, a lot of two-hop neighbor discovery. It's very interesting things, but it's active. There's no idea of stop looking. Your radio is silent between now and Wednesday. And therefore you have the same problems, which is the reactive rerouting. And this is more important in MANE environments where you probably are talking constrained devices. You've got that little loss because you've lost that link. Quick rethink, oh, it's that way. There's a loss there. And to go back to the point of, you could accidentally form micro loops because several things could spot that link failing at the same time, which means that initial stab at, oh, it'll go this way, could well be wrong. And then you get corrective and loop avoidance and loop back off kind of algorithms, which are exciting, but you haven't got a stable network service while all that's going on. And again, you've got that proactive discovery rather than proactive link reestablishment, which is wasting resources. And particularly in the MANE environments, that's not a problem. So you'll note that the key issues have kind of been copy and pasted between these two environments because I think they are common problems to both of them. Next slide, please. So a third answer that came out on the list is people said, oh, well, DTN can solve this. If you've got link outages, we can do store and forward. It's great. We don't have to worry about the fact we can, while we try and work out what the next thing is, if something goes off for 2 hours, DTN can save us. DTN is great. I am a chair of DTN and I can tell you DTN is great, but it's a transport protocol. It's for delivering data. It doesn't do routing. In fact, it's actually out of charter at the moment for various IETF political reasons, but, well, for scoping reasons, not political reasons. There are problems we still have to solve before we try and solve routing. And if TVR can come up with some of the routing problems, DTN will use it. DTN isn't an input to TVR. DTN, in fact, would like to see the outputs of something like TVR. So that kind of implies why I've started having these conversations at all. However, there is some interesting research that is not happening with the IETF and experimentation. And actually, I think fielded, I'm looking to see if anyone who knows this is willing to nod if any of this is live, particularly around what they call contact graph routing. So that's an understanding that at a certain point in time, two neighbors will see each other, and therefore we can start moving DTN bundles, they're sort of jumbo packets. Between them. And that's now become documented by CCSDS, which is a space governance community, and called SABRE, because it's a great acronym. Schedule Aware Bundle Routing. And the reference there for anyone who wants to look at it. And it's, what I find interesting is other communities are aware that having a schedule and trying to move things around based on the schedule is a good idea. So again, this is underlining, going all the way back to Kevin's point, which is this isn't new. And I think that's a good thing because it kind of underlines that I think we've got a problem here. So key issues about DTN. It's not a routing protocol. And the second point is it doesn't actually deal with IP. For those of you who are unaware of DTN, it's got its own sort of jumbo packet format called a bundle because of the nature of what DTN is. And please come to our session at 1 o'clock. It's great and learn all about it. Anyway, so that brings me on to really the potential work items. Because if we're talking about forming a working group, we ought to have some kind of discussion about what we should do. I think we should have a formal use cases document. It makes sense. I am a huge fan of putting fence posts around the scope is how I like to describe it. So you know quite clearly what's in and what's out because it's written down somewhere, because it kind of allows people to have a common view about what we're trying to achieve here. So problem statement, use cases, that kind of thing, to make sure, speaking as a chair, it's really helpful within a working group to be able to say, great conversation, not in scope. Let's get something to describe this bit because it most definitely is in scope. So I think a use cases document is useful. I think we should look at a general purpose solution for time variance and coordinate with other working groups who have the expertise on particular routing protocols. I don't think it is correct or effective for a TVR working group to say, we will write a BGP extension of some sort. I think that's completely incorrect. I think the TVR working group should look at understanding time variance and its impact on routing. And there's already discussions going on in the chat about what is a schedule? What should go in a schedule? Is a schedule a good concept? How do schedules get merged between nodes? We can solve that without looking at the particulars of individual routing protocols. But once we understand that and we've got information models, we have an understanding of what we will support with these schedules. Are we talking about link stuff, or are we going to talk at the end-to-end service stuff? You know, there's some interesting topics here. Once we've got that, we can go out to the link state routing groups, PIM if we want to touch multicast, you know, some of the MANE groups, whoever, and say, have you considered time variance as part of your protocol stack? If you have not, here is some information models and some functional operations around the creation, ingestion, introspection, updating, whatever of these information models that you might know an elegant way to include into your routing protocol using your relevant LSA, TLV, whatever you're using within your protocol stack. So it's, don't do it here, don't boil the ocean, in summary. So I know I'm running late and I'll be quick. What I did want to write down is what I think is out of scope, because this again is part of putting some fence posts, and this is personal opinion. It's a routing problem. Yeah, it would be great if applications knew all about it. Yeah, it would be great if we could get into all sorts of other things, but I think we have to start with step one, which is layer 3. Let's get the routing working, because everything else will build from that. And therefore, I think the following things get chucked out. And it doesn't mean that they're not really cool things to look at. I just think they're part 2 or 3 or 4. Store and forward. DTN's doing great stuff at the transport layer. Let's not go there. That doesn't mean talking about buffers and understanding the transition when something scheduled happens isn't in scope. But let's not talk about, oh, we could hold data for a very long time and then move it. Please leave that to transport and DTN at the moment. Have the discussions, but I don't think it's scope. Anything to do with making transport protocols schedule aware should definitely be a part 2 in my opinion. Don't want to start touching the transport stuff. Tuning TCP's behavior when you know something's going to fail in 20 seconds. Please don't go there. I mean, great fun, but we won't achieve anything. You know, it's a hard topic, and I think we need the groundwork before we can sensibly start addressing that. I don't think it's worth getting into, and I've said this earlier, how we create the schedules, how we do the prediction. I think we should start at, let's pretend we have a prediction. Let's pretend we have some kind of schedule. Can we talk about that? And then other people go back to your day job and work out cool techniques to create these schedules. Great fun stuff, but out of scope almost for the IETF, definitely out of scope for a working group who can achieve things. I'm going quicker. Multicast and multipath. Personally, they seem really hard. What's the last bullet? These are really cool topics, but I strongly suggest we focus on the basics first. The end. Yeah, no, it's absolutely fine. I was repeating myself.
Hi, Kevin Fall. After Lars's comment, it struck me a little bit that given what's happened in this kind of area in the past, when DTN work was a research group topic, we intentionally confused the acronym and its definition so that the D could be delay, disruption, whatever we want to have some research on would sort of be in scope. And I think what I'm hearing here is that, oh, that's like, we don't want that for sure. And so what is the scoping definition? So I think Lars said was sort of on the order of an RTT maybe. And so I guess to maybe try to refine that might be useful. What is this covering? And so just to throw out a couple, there was the use cases, we had space and so on. There's been underwater networks. The prop delay is 5 orders of magnitude worse than it is on RF propagation. So that's going to affect, if you had routing updates, it would affect it. Would that be the type of thing that would be in or out of scope? Because that's a world where you could have an end-to-end connection from the sender to the ultimate receiver, but the properties of the network underneath are pretty different than what we would normally do. So I guess what I'm not saying that's the one to worry about, but there's a few other features. When you say, RTT, that needs to be decomposed a little bit to mean like, well, really, what is that? And then if you're going to separate out the store and forward layer, which is okay, I suppose, but then it would be interesting to know what the communication, if you will, API is between those, because scheduling, back to the dynamic transshipment, all that stuff, that's very interested in knowing what paths, what links, what places there are, what storage facilities there are along the network. And one other one that I don't think we heard about is like properties of nodes along the way. And so at some point we had discussed some nodes being more reliable or more secure or located in certain geographies we trust or don't, and so on. And that would affect the routing decision as well. And maybe that's in or out of scope, but a lot of richness that had been discussed over the years and what you might want to use in your routing decision.
I think we're not going to have time to go into all the questions, but I think we should capture them and say these are items that we need to address as part of the working group or in scoping the working group. So thank you for that. I think I got some good notes on that. Please check the notepad to make sure we got it correctly. Brian.
Hello, Brian Cephas, PPL. One other thing that hadn't been discussed so far and is more of a gap analysis than a use case is on the management side. There are things like netconf that have this concept of a candidate data store versus a running data store. So there is a variation that's allowed, but you can't schedule it and you only get one of them. And so when the concept of multi-tenancy management comes into play, it really throws a wrench into things because you don't want to have a separate management organization for every single time something might change in the future. So just to ground some discussion in why you'd want to have a schedule for multiple things changing at their own time rates.
Yeah, good comment. In one of the earlier working groups this week, someone pointed out that there was a working group that spent a lot of time talking about how to document schedules. So, you know, there are good building blocks in other working groups that we definitely can leverage. Next, Torlis.
Yeah, thank you very much. So one of the questions we usually, or I'm trying to wrap up in my mind, is how do we get from here to some running code that does something useful, right? And I haven't seen very little, unfortunately, in the presentation that would give me a really good hint for that. If the way to get there is really mostly building a system out of mostly existing components in the IETF, plugging them together, the magical SDN controller that solves 99%, a good amount of data models, and then some app use of the routing system. That would be something that would be really good to show in some examples that's the goal. And then, I mean, we've got example working groups that have done this, kind of trying to build something useful with minimum additional work, combining what we've done in the IETF. My own Anima working group probably is something like that, right? So 99% of was just plugging together things, still a lot of work. So I'm not sure if that would then go into routing or ops, like they put Anima into ops, right? If this is really a little bit more fishing and we don't really know if we can come up with such a big, system design or something that really we are very certain will give value, then we also have fairly good experience, I think, by now with the special interest group model that we're using so far primarily in ops with MOPS and IoT ops, right? So that puts you into more constraint about what you're supposed and able to write in RFCs. So just as process recommendations of where you might want to look into going the next steps, making proposals toward some form of a working group.
Yeah, thanks for that, Torlis. Certainly, after this meeting, we're going to take all the feedback, work with the AD, the IESG, and even the IAB on what's next. What you see here on the screen actually came with input from Alvaro of make sure that what we come up with is attainable and actionable, right? We can go deliver something. And it's probably a Yang model or an information model. And when we succeed at this, we can talk about what happens after that.
Yeah, so just as a personal contributor, I like the components, right? But I'd be a lot more happy if there's some place that says, and here is how these components can be mixed together to build a system that actually delivers value. Because just starting out throwing components, against the wall,
I see that as
is required but not sufficient, right?
I would see that as an objective. That comes under the approach framework result. It shouldn't just be here is some stuff. It should be here is relevant pieces and how they go together. This is almost a recipe for you.
Yari?
Yari. So I like this. This is really cool stuff, and we should definitely do this. Has a lot of interesting different use cases, and yeah, I mean, we should go ahead. The only caveat that I would put on this, or a sort of little worry, is that there may be some sort of a chicken and egg problems hiding here. And I actually got on the line before before the statement was made about schedule creation being out of scope, and that's a good thing. And indeed, like you have this local and global optima, and you deciding what you're going to do with your node may not actually, like your local optimization may not be what you actually want for a lot of these cases, particularly when it comes to things like energy. And energy is also sort of an interesting, complicated case because you have so many, like it's as was noted, it's pretty broad. So you have, you know, different aspects to worry about, but also that you have different techniques. You have, for instance, implementation techniques where you can put nodes into like a relatively low power sleep states where they can still act as part of the network. You don't have to tell anybody that you're sleeping, but you can still save a huge amount of energy, or you can be sort of totally off and not respond to anything, and then you have to tell the rest of the network. So I think some of the use cases are sort of really straightforward, that like a satellite is forced to go on a rotation around Earth and you exactly know what's going to happen. Some of the other stuff where you start to compute that, well, you know, there's these criteria and these costs and so on, and they interact in interesting ways across parts of the network, then that gets more complicated. But yeah, so my advice is to stay as focused as possible. Don't try to solve everything, just like the really simple case, and deal with that, and let's move on.
Thank you. Adrian?
Hi, Adrian Farrell. Thanks to the proponents and the chairs for really putting this together. I want to agree and disagree with Lars. I want to agree that part of this problem space is the time variant provision and awareness of service points and direction of transport paths. And I want to disagree because I think this is about packet routing and routing inside the network. And you know, the transport is an overlay over packet routing. And we need to look at both of these problems, or maybe all three of these problems, in our analysis and work out which ones we are solving, and then work out where to solve them, and not just use the existence of one problem to say, well, you can't talk about the other problem.
Thanks.
Dejan Bogdanovic. So just to clarify from a previous point, time variant routing is an interesting problem, but let's not it become kitchen sink for everything else.
100% agree.
That's the one thing. Let's define very clear problem that you want to solve and that we can solve. For mesh networks, so as long as you have a finite topology that you are managing, that's a single management domain, then having a number of variations of your topology that will be changing on the schedule, whatever the schedule might be, that is being defined by that one management domain owner, that's a problem that can be pretty well defined. But if we try to add all other possible things in, we will get nowhere.
Can I respond quickly? Yeah, I 100% agree with you for two reasons.
That's about as quick as you got?
Oh, no, I'm going quicker.
We're out of time, so.
You can't
Colin?
schedule the whole internet. And second of all, we only have bandwidth to achieve something achievable. So let's try and achieve that.
Yeah.
In full agreement.
Colin, and I saw Lars come up, and I don't know if you want to preempt the queue blockage. Okay.
Hi, Colin Perkins. Colin Perkins with no hats, let's be clear. This is an area where obviously there's been a lot of previous work and a lot of previous research. I agree that it perhaps seems reasonable to try and explore whether we can do a focused standards activity here. You know, it's time to maybe narrow this work down and see what's feasible. I think I'd echo, I think it was the comment Lars made. Think about the amount of time variance and the amount of link latency you have in the network and draw bounds around what you're going to consider, because it makes the scope feasible. It also tells you whether you need to solve the transport problems or whether you can use existing transport. I'd also say there are obviously many different types of time varying networks. You know, the low Earth orbit satellites are one which seems popular these days. Kevin, I think, mentioned underwater networks. Some of these have radically different properties and need radically different amounts of domain expertise. So before picking a particular scope, I would urge the group to make sure it's got people with the relevant domain expertise, just in case you accidentally miss something.
Yeah, that's
sure it
certainly a pretty
generalizes.
important point about make sure we have the right people. So we have 6 minutes left. The plan is we're going to do 3 polls. They're already in the chat if you want to see what them coming. And then we're going to turn it over to ask the AD and our IAD advisor if they have anything to add. And then we'll probably close out. No, we definitely will close out. Sorry, I should say probably. So I'm going to get the first poll going. Should have had that queued up, sorry.
Could you put the polls on the screen?
Yeah, getting there. Sorry. So the first question, should we be working on this in the IETF? We're getting, I think, a lot of positive response. Certainly more than half the room has said yes. A few have said, I'll take the lower the hand as no, but I think that's pretty clear. We're going to move on to the next question. The next one is do we need a new routing area working group to work this problem? That's not to say there won't be other working groups in other areas to deal with like transport, but we're focusing on the routing piece, which actually I agree, I don't remember who said it, might have been Adrian, we're about delivering packets. New group and routing area is the question. Do you think there should be one? So again, we have a good percentage of people responding. That's always a good thing. But this time we have more of a split, but still the majority are saying yes. We're going to move on to the last question, which is almost the most important one. If I can find the button. Which is, are you willing to contribute? And contribute can be a reviewer, it can be an author, but basically show up and do work. If we don't have this, there's sort of no point in the other two. So I think here too, it's very similar, although there's, I'm actually a little confused by the results because the previous one, it felt like there was more opposition. And this one, we have like more people say they're willing to show up and do work. So I guess this is the most important item. So with that, I would like to, so I see a IESG member getting up at the mic. I'm going to ask if he's asking, is he coming as IESG? Or, okay, if you're coming as IESG, go right ahead. If you're coming as a contributor, please sit down.
Sorry. I think we just need to remember that, you know, obviously these aren't votes, you know, they are an indication. And I think my reading of this, and this is from what I'm seeing here, is that people are saying maybe it shouldn't be in routing for the last one, but at the same time, if it is, we're still prepared to work on it. That would be how I would read that. Yeah, so that just from, from an AD perspective, how we're evaluating this, that's how I would read that.
Yeah, I think it's reasonable because, for example, I think the answer is we should have multiple working groups because I think there's multiple problems. So I could see if someone thought it was either or that. So with that, I'd actually like to ask Alvaro, and I think Mallory, I think you're our IAB advisor, if either of you would like to say anything, and if you don't, that's okay too.
Sure. Alvaro Rotano, Routing AD. First of all, thank you everyone for coming today. I think 134 people still at the end is a lot of people. It confirms one of the reasons why we wanted to do this BOF is their interest in the problem. And of course, the poll have demonstrated that there is interest. People think there is a problem to solve. People are willing to contribute. Thank you to the chairs, of course, for running this, to the proponents. Everyone, I'm going to just say the obvious that everyone has been saying. We need to scope down the problem. This was a non-working group forming BOF, which is precisely to gather use cases, to gather interest. The area of potential application of TVR, as everyone has said already, is very, very wide. We need to narrow down, we need to scope whatever we're going to do or can do in the routing area or potentially elsewhere to things that we can deliver, that we can work on, that are going to be clear. So that's what I would like to see being discussed in the mailing list going forward. What are the, I don't know, 1, 2, 3, whatever deliverables that we can go and try to move forward. And as we see that discussion, we're going to evaluate that and figure out what the next steps are going to be after the discussion. So again, thank you so much.
Thank you.
Mallory Nodal, Center for Democracy and Technology. I think Russ also was here from the IAB, and so it's not only me. But I guess so because I'm not a domain expert, as I sort of look at the BOF, some of the questions I recall from the things we evaluate I'm going to focus on where else is this work happening. I saw earlier in some of the presentations, some of this is ITU related. All of that is going to be really helpful information for me as I go through that questionnaire. So anyone who wants to, I would say I will appreciate anyone who can respond to some of my questions. Maybe I can talk to you all as the delegates about those sorts of things that I don't quite understand. But that's sort of the nature of the review that we do. But it's great to see all the interest. I think that's a strong sign. Thanks.
Thank you. Certainly, we're happy to talk with you offline. And anyone to follow up, I put in the chat the link to the group area. You can find there the archive as well as how to join the list. Please join, start contributing. We really appreciate to continue the good energy that was here today on the list. And we'll work with the ISG and the IAB on next steps. And thank you all for, I think, a very successful session of TVR. Hopefully see you in Yokohama.